Right, hello everybody. So this is the lesson on rate of decay. We learned in the previous lesson that there are various types of decay. And decay happens because the nucleus becomes unstable. Now we want to actually monitor how long is a sample of radioactive material going to last? How long is this radioactive material going to last? That is what we are studying now. So I want to start off by looking at this graph right here. So if we analyze the graph, we can see that we're talking about cobalt 60. It's decaying over time, meaning that it's radioactive, meaning that it's emitting particles, emitting energy, and its mass gets reduced, right, because of that radioactivity. Now, on the y-axis, we can see cobalt 60 remaining. So how much of it is remaining? On the x-axis, there's something called the number of half-lives. We don't really know what that means yet, but you will in a bit. And it also says that one half-life will last 5.27 years. So if we go to the notes, it says that a half-life is the time that is required for half of the sample to decay. So for example, in this graph, we are starting with 10 grams of cobalt 60. It's radioactive, so over time we're going to have less and less and less of it. Now, according to the definition of half-life, after one half-life right here, half of the sample will disappear. So it goes from 10 grams to 5 grams. Then after another half-life, here, you're going to have half of that. So instead of 5, now you have 2.5. And then after another half-life, you'll have half of that. And then after another half-life, you'll have half of that. So after 5 half-lives, this is how much you're going to end up with from the original sample. After 3 half-lives, this is how much you're going to end up with, okay, during the duration of these 3 half-lives. So if you look at each half-life, here is one half-life, that is going to last 5.27 years. So after 5.27 years, you're going to go from 10 grams to 5 grams. And then if another 5.27 years elapse, then you're going to have half of the sample again. So each half-life is equivalent to the duration in which half of the substance disappears. And it's very useful to scientists to understand how long a substance is going to last, and then how much of it are we going to have. You know, in medicine, we want to know how long a medication will last. How long is a radioactive sample going to last if we want to make energy out of it in a nuclear power plant? So that is why it's useful. Everything that I just said is written right here for you, so I would read through this just so you guys understand the concept of the half-life. It says you have iron 59. It has a half-life of 44.5 days. Okay, so what that means is that in order for half of the iron 59 to decompose, it's going to require 44.5 days. Okay, so I like to personally write that down. Let me put that marker. Here you go. So one half-life is the same as 44.5 days. According to the question, it says you have a 2.00 milligram sample. So that's what you're starting with. After 44.5 days, you'll have half of that. Okay, so what we do is we look at what the question's asking for. It says how much would remain after 133.5 days. So in order to figure that out, we first have to figure out how many half-lives this substance will undergo. And what we do is we start with the amount of days that will pass, which is 133.5 days. And we know that for one half-life, oops, so this one, my bad, half-life. For one half-life, 44.5 days will elapse. And if you do the math, you get 3 half-lives. So you're going to go through 3 half-lives. So what that means is we're going to call this our starting a half-life of 0. So our half-life, we're going to track it here. So after one half-life, we're going to have half of this. So it's going to be 1.00 milligrams. Okay, after a second half-life, we're going to have half of that. And then after a third half-life, you're going to have half of that. So we are interested in seeing how much sample is going to remain after 3 half-lives, because in 3 half-lives, you have 44.5 days that have passed. So if you look at this chart that we just made, after 3 half-lives, that's how much of the sample is going to remain from our original amount. Okay, so let's do this again using the next example. Example 2. Here we go. Example 2. Here we go. Okay, so it says gallium-68 has a half-life of 68.3 minutes. So again, I like to write what's given on the side. One half-life is equal to 68.3 minutes. How much of a 10-gram milligram sample is left after one half-life? How much is left after 2 half-lives? How much is left after 3 half-lives? So we're going to call this half-life of 0. So this, at half-life of 0, which is our starting point, we're going to have 10.0 milligrams. After one half-life, which is 68.3 minutes, so after 68.3 minutes elapses, which is really quick, right? You're going to end up with 5.0 milligrams. And then after a second half-life, so another 68.3 minutes, then you're going to have half of that. Okay, and then after another half-life, a third half-life, you're going to end up with half of this, which is 1.25 milligrams. So the question says how much will remain after the first half-life. This is how much remains after the first half-life. This is how much happens to be left after the second half-life. And this is how much happens to be left after the third half-life. All right, so let's do the third example. Third example is right there. If only I could get my pen. Where are you? Here we go. Third one, right there. Okay, so it says, if the passing of 5 half-lives leaves 25.0 milligrams of strontium-90 sample, how much was present in the beginning? Okay. So for this one, it's saying that after 5 half-lives, you end up with 25 milligrams. And what the question is saying is how much was present in the beginning. So we're kind of working backwards here. So I am going to do that. I am going to write 25 milligrams. And that occurs after 5 half-lives. So that means that I'm going to work backwards, and it says how much was present in the beginning, and that implies 0. So I'm going to, instead of divide by half, I'm going to multiply by 2. So 50, 100, 200, 400, and 800 milligrams. So at the very beginning, I ended up with 500 milligrams because, after one half-life, you're going to end up with 400. After a second half-life, 200. You just keep reducing it in half. We don't really know the duration, which is fine. We don't need that. But this is the way you would do it. All right, so let's do example 3. If you want to try example 3 on your own and then check in, you could do that. So it says, example 4, polonium-214 has a half-life of 163.7 microseconds. So that means that half of that sample will disappear very quickly. Like, it's not even a second, it's like microseconds, like really, 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 really quickly it will disappear. And so I'm going to write it down. 1 half-life is equivalent to 163.7 microseconds. So micro is this symbol right here. How much of a 1.0 gram sample will remain after 818 microseconds? So in order to do this, we're gonna make our chart. We're starting off with 1.0 grams, and the half-life will be 0 because it's our starting point. After the first half-life, after 163.7 microseconds, you're going to end up with half of that. Then after a second half-life, you're going to end up with half of that. And then after a third half-life, you're going to end up with half of that. And then after a fourth half-life, you're going to end up with half of that. And then after a fifth half-life, you're going to end up with that much. So according to the question, it's saying how much will remain after 818 microseconds. In order to do that, we need to figure out how many half-lives will pass. So we want to know, we have 818 microseconds. We want to know how many half-lives that is. And it says that in 163.7 microseconds, that's the duration of one half-life. And when you do this, you get 5. So after 5 half-lives, it'll tell you how much will remain, which is that much. So that much grams of polonium will remain after 5 half-lives, which is, again, 818 microseconds. Okay, so that's how you would do that one. That one's a little tricky. That one's a little tough. You should do this first. So I know I did this first, but you want to figure out how many half-lives are going to be present in a certain amount of time, which is 818. So after 5 half-lives, then you start reducing it in half until you reach 5, and that's how much will be left over. Okay, so next one, example 5. You should try this one, then check in with me. Okay, now that you tried, Let's do it. So here we go. It says you have a half-life of that is equal to 1620 years. So in order for half of this substance to disappear, it's going to require a lot of time, like 1,620 years compared to microseconds. That's a lot of time. So radium doesn't really decompose much. It's not super duper quick in decaying. It's going to be a very gradual process. It says that how much of the 50-gram sample will remain after 3240 years. So we need to figure out how many half-lives will be required or will undergo for this sample. So we have 3240 years. In 1,620 years, you have one half-life. And you end up with two half-lives. Okay, so after two half-lives, the question is asking for the amount that will remain in two half-lives, which is 3240 years. So we're going to start 50 grams, 0 is our half-life. After one half-life, which is 1620 years, you're going to end up with half of it. After another 1620 years, you're going to end up with half of that, which is 12 point. Ooh, can't even do basic math. Which is 12.5, right? So after two half-lives, that's how much of the sample will remain. Okay, so that's how you do that one. Okay, go ahead and try example 6 and then check in with me. All right, so it says how much of a 58-gram sample of radium-226 will remain after 3 half-lives? How long will the process take? So we have 58 grams and we start off with that much, right? So the half-life is 0. And the question is saying how much will remain after 3 half-lives. So after one half-life, you'll have half of that, which is 29. After two half-lives, you'll have 14.5, and then you'll have 7.25. Okay, so that's how much of the sample will remain after 3 half-lives. How long will this process take? Well, if you look at the previous example, it says that one half-life is equivalent to 1620 years. Now, if it takes 3 half-lives for this amount to remain, then you guys can use basic ratios, right? From 1 to 3, so we multiply this by 3. So 3 half-lives will be equal to 6480 years. Okay, or you could just use a conversion. 3 half-lives, 1 half-life, 1620 years will equal to 6480. Okay, so that's how much time will elapse from here to here. Okay, so let's try the next one. The next one's a little tough, so go ahead and try that one, and then check in with me. So it says you have, okay, now that you tried, hopefully you tried, you have 120 grams of this sample. It decays for a period of time, right? So this is half-life of 0. How old would a sample be if 3.75 grams remained? So what we're going to do is we're just going to keep dividing by half until we end up with that amount. Right, 7.5, 3.75. So if we look at this chart, we can see that it required 5 half-lives. So 5 half-lives were necessary for the sample to reach 3.75 grams. But the question is saying how old would the sample be? So we want to convert half-life into time. And if you look at the previous example, one half-life is equivalent to 1,620 years. And when you do the math, you get this many years. So that's how much that would be the age of the sample that we initially had in the first place. All right. And the last thing is this. There are two types of nuclear reactions that produce a huge amount of energy. The first one's called nuclear fission, and you guys can read about that. Basically, this is what nuclear power plants do to make a huge amount of energy. And we usually use neutrons, so neutrons slam into a very heavy nucleus and it triggers a burst of energy to be released when the nucleus is split into fragments. And you guys can look at Google Images and see a picture of how that looks like, and it triggers a chain reaction. So after one atom is broken into fragments, then the neutrons are released, and then more and more and more atoms start to split, and a big burst of energy is released. And that's how nuclear power plants work, is they use that energy to harness what we need for our demands. And the issue with this is that it requires a lot of care, a lot of monitoring, because if you don't monitor the neutrons, then you could undergo a nuclear meltdown, just like it did happen in Chernobyl, Ukraine, where there was an explosion because people couldn't control the amount of neutrons that were present in a chain reaction. So we typically use control rods to monitor that. But again, any error can lead to danger. And so that is why we don't really have nuclear reactors in the first place, but some countries do use them. And nuclear fusion is another type of reaction. It's basically when you combine hydrogens and you form helium and it releases a burst of energy. That's basically what the sun does. However, us in the US, we actually built a hydrogen bomb, and that is the process that is used within the bomb, where hydrogens form helium and they release the burst of energy, and then it could be used as a bomb. And so the problem with this is that it requires a lot of energy. For this process to occur, it requires a lot of energy, a high activation energy. So using nuclear fusion for our energy needs is not really realistic because of the amount of energy that you need in the first place. Okay, so that's that.